Hello. Hello. Yes. Sorry for the delay. Uh, Welcome to week 12 live session. This will be the last week. I'm Sai Dinesh. I'm the PMRFTA for this NPTEL course. I'll be covering the material from week 12, and we'll be discussing some assignment questions as well. Okay, so let's get started. Okay, so in this lecture we will be talking about discrete Fourier transform, it's known as DFT. Okay, so before we talk about that, so let's just briefly review the old ones. So first we see that there is a continuous. So let's briefly go to the previous ones, which is continuous time Fourier series, right? So in this case we have a continuous and periodic signal x of n, sorry, x of t, which is also equal to x of t plus t, with that is the time period is t. So this x of t is can be represented as a summation of sinusoids, complex sinusoids, k equal to minus infinity to infinity a k e power minus omega naught t, where this coefficients a k is 1 by t minus t by 2, 2t by 2 x of t e power minus j omega naught t into dt. So continuous periodic is giving this continuous periodic is giving discrete a periodic Fourier series. Okay, so the next one is, so this is the first one. So the next one is continuous time Fourier transform, continuous time Fourier transform, which is, so this is actually one important Fourier expansion, which is the DFT that we are talking about will actually be somewhat related to that, but not exactly. Okay, so continuous time Fourier transform x of omega is equal to minus infinity to infinity x of t e power minus j omega naught t dt, and x of t is 1 by 2 pi minus infinity to infinity x of omega e power omega t d omega. Okay, so here it is continuous a periodic, this will give periodic continuous, sorry, a periodic continuous. Third one is discrete Fourier transform, so also known as DTFT. So this is what we have been talking about the entire course, basically DTFT and the Z transform, right? So x e power j omega equal to the DTFT of signal x of n is equal to summation over all x of n e power minus j omega n from n equal to minus infinity to infinity. Excuse me. X of n, and the x of n is equal to 1 by 2 pi minus pi 2 pi x e power j omega into e power j omega n dw d omega. So here it is discrete periodic, so this will be periodic but continuous. So this is what we have been talking about, but this periodic continuous since it is continuous, the signals that we will be working on are discrete signals, right? So only then they can be stored, but the Fourier transforms is continuous, but continuous values cannot be stored in a computer. So stored in a computer, hence DFT comes into picture. The DFT comes into picture. So before that, there is one more thing also called, like continuous Fourier series, there is discrete Fourier series, also known as DFS, which is x of n is equal to k equal to 0 to n minus 1 ak e power j 2 pi k by n into small n, where again ak is 1 by n, summation from n equal to 0 to n minus 1 x of n e power minus j 2 pi k by n into small n. So this is discrete Fourier series. But also note that, and also you may note that this exp exponential of e power j 2 pi into capital N into k has only n distinct exponentials, right? Yes, so this is one thing. So discrete Fourier series. Okay, here it is discrete and periodic. So here also we have discrete and periodic. So since it is discrete and it is periodic, we will be able to store that. In computer, since it is since it is periodic, we can only save one period of the sample of the signal, right? So yeah, that is one thing. So the properties of DFS, if we maybe we can okay. So this is what we have seen. So we have x of n with DTFT x e per j omega, but it is continuous, right? So let's say we have some signal x of n like this. Discrete and aperiodic. So this will here give a so 0 to n minus 1. Let's say this is an n length sequence which is aperiodic. Since it is finite, it means it is aperiodic, and this will give a continuous and periodic DTFT, right? But this cannot be stored. So what do? We try to write it down formally. Since we cannot store the DTFT which is continuous, we try to sample it. So remember that all these are intermediate steps, and this actually we do not actually do all these steps in practice to find EFT. Okay, so we try to sample it. So if we sample it, right, let's say, okay, I'll draw it once again. Right, this has is 2 pi. So we sample it. Okay, so this is, again, let's say this is n samples. So this is n samples, right? So we see that sampling in one domain causes periodic repetition in the other domain. We know that causes in another domain. So this sampling, so x of n is periodically repeated by 2 pi by 2 pi n equal to n samples, meaning 0 to n minus 1 and 2 to n minus 1 are periodically repeated. Here it is 2 pi by n. Sampling is done at 2 pi by n rate, meaning like in the interval of 2 pi, oh, so in the 2 pi interval we take n samples, meaning the sample spacing is 2 pi by n. So if we sample the frequency domain by 2 pi by n, this causes a n sample periodic repetition in the time domain. So here it is, so now it is discrete periodic, and here also it is discrete and periodic. So we can store this in the computer by storing the values of one period we can say, like, because we are talking about frequency domain also, so about one period. Right, so this is actually DFT, right? So in DFT we only talk about a finite duration of finite duration signal x of n from 0 to n minus 1, and we take a n point DFT to get a n sample Fourier transform, which is the n point DFT. So x of n is 0 to n minus 1, and this has zero 2 pi by n into n minus 1. So both are n points in both discrete and time domain and frequency. So this is n point DFT. Okay, so the x of k is written as n equal to 0 to n minus 1 x of n e power j 2 pi by n kn. N equal to 0 to 1, and the x of n is 1 by n k equal to 0 to n minus 1 x of k e power j 2 pi capital N into n. So here k equal to 0 to n minus 1, here n equal to 0 to n minus 1. In both time domain and frequency it is n samples. So this is what DFT is. Okay, so some of the properties of DFT, you can say. Let's talk about some properties. Keep writing as DFT, right? So let's say x of n has x of k, x of n on this side has n times of that of the this, and this is duality. Okay, so and then second is shift. So another one more notation is Wn is equal to e power minus j 2 pi by 2 pi by n. So this is one notation, Wn. Okay, so next linearity, which is a times x1 of n b times x2 of n will give a times x1 of k b times x2 of k. Next, x of n minus n, which is shifting. So this actually implies circular shift, because we are only talking about a finite duration signals. Excuse me, we're talking only about a finite duration signal, and the rest of it is not defined. We do not make any assumptions about the signal from after n minus 1. So signal is only defined in the range 0 to n minus 1, and the DFT is also stored in endpoints, which represent 0 to 2 pi by n into n minus 1, which are endpoints finally. So this is circular shift. So if we circular shift the signal by m, this will actually become e power j 2 pi by n m k into m the x of k, or wn, so this is minus wkm into x of k. So this is the shifting property. This means circular shift. So now, and one more thing, and the next one is, let's say instead of shifting in time domain, we shift it in the frequency domain. So x of k minus L of n, which is circular shift, then this will be wn minus ln into x of n, is the shifting property, right? And now one important property is s1 of n circular convolution with x2 of n will raise in the frequency domain multiplication of x1 and x2. Okay, right? So this is circular convolution, which is equal to m equal to 0 to n minus 1 x1 of m x2 of circular shift of n minus m. This is equal to, so this is the periodic circular convolution or periodic convolution. So this is really important. So in DTFT, x1 of e per j omega into x2 of e per j omega causes linear convolution x1 of n since times x2 of n. But here in DFT, x1 of k times x2 of k causes circular convolution, which is x1 of n circularly convolved with x2 of n. Okay, and then one more property is that x star of n will give x star of k. Okay, yes. Now, so these are the properties of DFT, right? So let's do some assignment questions, right? So question 1, let x of n be defined over the range of 0 less than or equal to n less than or equal to n minus 1, and no assumption is made about x of n outside 0 less than or equal to n less than or equal to n minus 1, right? Now let x of k be the endpoint DFT x of n, which means x of n endpoint DFT x of k. So the inverse endpoint DFT of x of k is periodic with period n. Is it true or false? So we have seen earlier that in discrete Fourier series, both of it is discrete periodic so, and length of signal equal to n and endpoint DFT. So there is no, so this is what it means. Next question. Question 2. Question 2. The condition to recover DTFT from the L point DFT for an L length discrete time sequences is what? So we have seen that. Sampling in one domain causes periodic repetition in another domain, right? And also we have seen that 0 to n minus 1 2 pi we take so n samples in frequency domain causes n periodic signal in the time domain, right? So what should L be? for the signal not for signal not and x of n not to be aliased. Question 3. X1 and x2 are two different n length sequences. So x1 of n, x2 of n are two different length n sequences, right? And the n point circular convolution. So n point circular convolution is same as convolution. So x1 of n circularly convolved endpoint gives rise to y of n, which is endpoint. But in convolution, x1 of n linearly converge with x2 of n, endpoint y of n plus n minus 1 points. Or I'll just write it as nth. Question 4. Question 4 is, if x of k is endpoint dft of x of n, x of minus n will have if x of k terms of n, what is it? Now we have seen that x of n minus m has wn km times x of k, right? So we apply change of variables and verify. Question 4. Sorry, this is question 5. x1 of k multiplied with x2 of k results in ADFT. Question 6. Say x of k is 1 j minus 1 minus j, be the dft of four length sequence, right? So then what is j power n into x of n solution? So we know x of n causes, so if x of n and x of k are DFT pair, then we know that Wn minus ln of x of n causes a periodic circular shift of L samples. Now j is equal to e power j pi by 2 per j pi by 2. So j power n x of n is equal to e power pi by 2n into x of n, right? But n equal to 4. Let's write e power j pi by 2 n x of n as e power j 2 pi by 4 into n into x of n. So e power j 2 pi by n into x of n. So 1 second. So j power n x of n is equal to e power 2 pi by 4 into n into x of n, which is equal to power j 2 pi by capital N into x of n into x of n, which is w n into n times x of n. We know w n ln x of n has a circular shift of L samples. Here L equal to 1, which implies DFT is shifted by one sample. Okay. Okay, I'll remove. No. Next, question 7. It's end. X of n is 0, 1, 2, 3, 4, 3, 2, 1, 0, 0. Then x2 of n is 3, 2, 1, 0, 0, 1, 2, 3, 4. right? So this 0 is gone here. X2 of n is x1 of n shifted by 5 samples, right? So find the relation between x1 of k and x2 of k. Refer to properties. Next one would be question 8. Let x of n be a 6-length sequence 1 0 2 2 3 1, and its DTFT given by xe per j omega, right? So it is sampled at every pi by 2, which implies 4 samples in 0 to 2 pi. Then 4.id ft is, so if we as we have seen earlier, taking n samples in the frequency domain led to a n point periodic shift in the time domain, which implies 4.4 samples in the frequency domain will lead to 4 point shift in the time domain. Find the new x1 of n. Next 8 questions done, right? So this is question 9. So consider two finite length sequences x1 of n, x of n. So we have x1 of n for 0 less than n less than 8, x2 of n 0 less than n less than 19, it is 9 point and 20 point. Let IFN denote the 20 point circular convolution of x1 of n and x2 of n over what range of n will y of n be equal to the linear convolution of n, linear convolution of x1 of n and x2 of n, right? So solution, we see that x1 of n has samples up to 0 to 8 and x2 of n has samples up to 0 to 20, right? So now linear convolution means if y of n is equal to x of n, x of m, x2 of n minus m over all m. Circular convolution means y of n equal to m equal to 0 to n minus 1, x1 of m, x2 of circular convolution of m, circular shift by m, right? So for 0 less than n less than 8, let's say, so linear convolution is x1 of m x2 x, okay, I'll write here 0 to minus 19 of x2 of m if x2 of n minus m means n 0 minus 19 plus n, right? This is, so where will this overlap equate to that of the circular convolution? So 0 less than n less than 8, 9 less than n less than 19, and 19 less than n less than 27. Question 10 means we have x of n equal to sine omega naught n for omega naught equal to pi by 5 for 0 less than n less than 9, right? So 10 point x of n, right? So we are saying y of n is equal to x of n and 0 for 0 less than n less than n and 10 less than n less than 19. So extended to 20 points by 0 padding. So what does this mean? So x of n, if we take a 10 point DFT, we get x of k. It is 10 point not equal to 0. So the real part, is it equal to 0? No. Now next one is, so next find the peak value of x of k. For option 2. Now y of n is 20 point, therefore if we do if we do 20 point DFT, what will it be? So this is basically, so if we have x of n with a DTFT of xc per j omega, if we sample 10 points in 0 to 2 pi, we get 10 point DFT, and if we sample 20 points of xc per j omega in 0 to 2 pi, we get 20 point DFT. So the underlying DTFT is the same. This is for the third part. The fourth part is also, like, you can verify. Next is the last question is, we have x1 of n 1 2 1 1 2 1 1 2, x2 of n is 0 1 3 2, right? Saying n equal to 8, meaning x2 is 0 1 3 2 0 0 0 0 4 0 padding, since for an endpoint circular conversion, both must be endpoint signals. Find IFN is equal to 10 minus 1 x1 of m x2 of circular shift of m samples in x2 and multiplied with x1. That's it. So this is the 11th question, which is pretty straightforward. Just need to find the values. If you want to verify, then you can do that in MATLAB as well, right? So yeah, so in this lecture we have talked a few topics about DFT, how we arrive at DFT and why DFT is important, and then we see some properties of the DFT, and then we go on to solve the assignment questions. So please let us know if you have any doubts. Please post any questions in the discussion forum. We would be happy to help. Okay, thank you so much.